We're here to share with you a little bit about our experience in supercharging our campaign engine at Marketo using Akka. Before we go into our Akka journey, I just want to give you a little context and background on Marketo and campaign engine. So what do we do at Marketo? Well, we offer the leading engagement platform that allows marketers to grow revenue. We integrate with CRMs, we do email marketing, campaign and lead management, web tracking, nurturing, scoring, analytics, and so much more. We have thousands of customers across more than 50 countries who use our services today, including Microsoft, GE, Panasonic, and Charles Schwab. And a great deal of that is driven by our campaign engine at Marketo. So it's a pretty crucial piece of technology for us. So what is exactly campaign engine? At a high level, our campaign engine is an event-driven framework. We allow customers to define a set of actions from a library of over 50 predefined and customizable actions, and a set of rules for when those actions should happen based on events occurring within their instance. This allows our customers to define fairly complex business logic using a marketer-friendly user interface. So before I give you a concrete example of what that looks like, I'm going to just define a few key pieces of terminology. First off, a lead. A lead is basically an instance of a person object, as in a person that one of our customers may be trying to market or sell their product to. An action is one of 50 or more operations that may act on a lead. For example, sending an email, syncing to a CRM, changing a data value on the object, etc. A campaign, or more specifically a trigger campaign, is a set of 1 to n customer-defined actions that occur on event listeners. And then finally, a task. To tie this all together, a single task is a set of customer-defined actions that run on a single lead, as is defined by the customer in a campaign. So that may sound a little bit abstract still, so let's just look at a concrete example of a form responder trigger campaign that a customer may define with a little bit of extra scoring logic. Here we can see a definition of a trigger here in orange. This means when a lead fills out a form, we would try to trigger the work that's done in this campaign. The green filters here would be applied to allow a user to define or target a more specific set of leads. For example, here, we want to make sure their email address is not empty so we can send them an email. We want to make sure we haven't already sent them the email, and we want to make sure that they're not on the blacklist. Here is where we can see the definition of the campaign flow, which is the list of actions that we need to actually execute that are defined by the customer. The actual execution of a campaign is composed of many different campaign actions. A marketer can even dynamically choose between the different actions based on some conditions, as we see here in the first step. It's similar to if this, then that, but our users can chain many different actions together, and they can combine conditions within an action and chain actions to shape the flow of a campaign from one action to the next. And we need to do all of this at scale. We have one customer with more than 5,000 different active trigger campaigns listening on all the events happening within the system. We have another customer with more than 100 million unique lead objects that are all tracked. And then finally, our system handles over 20 billion trigger campaign jobs every month. A little bit about our legacy system, part of our motivation as to why we started our Akka journey. We had a group of 200 customers being served by 6 schedulers and 3 dispatchers and 36 executors. We had just a simple round-robin dispatching with time quantum for fairness, with additional partitions available for large customers. But problems with our legacy system, we were not at the time leveraging multi-threading efficiently. Resources were only shared across a subset of our customers. We were definitely underutilizing database resources, and we found it was hard for us to scale up our system independently. So with that, I'm going to hand over to my colleague, Pei.
Thank you, Dennis. So we started the journey about 2 years ago. So we like to, Our mission is to find a solution that can help us scale with the growth of our business. So we were looking for technology that can help us scale horizontally, handle fault tolerance with a self-healing, create a responsive system, provide fairness and elasticity to tenants, handle back pressure, ensure exact once execution, preserve order for tasks to the same target. So after evaluating some technologies in the industry, we finally landed on Akka technology. The reason we chose Akka was because Akka Cluster gives us horizontal scalability at cluster level. Cluster, shard, auto-balance, we recreate, give us a fault tolerance at the shard level. Actor supervisor strategy gives us fault tolerance at actor level. Actor persistence gives us a self-healing capability at actor level. And at least once delivery gives us fault tolerance at the message level. So from that, let's start with the design of our actors. We followed the best practice of actor domain-driven design to model our business. We generalized the actor hierarchy and actors' responsibility to keep things simple. From the top, we have tenant actor, which has incur and decur child actors. On the decur, we have a number of executor actors. We can further parallelize the process for a tenant, but for simplicity reason, let's keep it simple, single instance per tenant. So by applying actors as supervisor strategy, we are able to get fault tolerance from the actor hierarchy design. Tenant actor supervises child actors, in this case it's incur and decur. And decur actor supervises child executor actors. So how about fairness among tenants? How do we handle it? We use number of executors to proxy the execution bandwidth for a given tenant. Among tenants, we keep fairness by giving them same number of executors. And how do we handle elasticity for a tenant? With a reactive system, we are able to dynamically scale up and down the execution bandwidth for a given tenant at runtime. So this also empowers us to do auto-scaling and tier pricing in the future. For back pressure handling, we only need to handle it between incur and decur. In push mode, a message is sent directly through to dispatcher, to incur to dispatch. In pull mode, a message is incurred to a persistent store. So between incur and decur, they will handshake to switch between push-pull modes. So for partial order preservation, which is a unique business requirement we have for trigger campaign execution, so we like to execute tasks to the same target in the same order as they came in. So if we have task 1 to Jane, which was already sent to executor number n, we'd like to send task 3 to executor number n, since task 3 is also targeted to Jane. Even though executor number 2 is available to process any task at this moment, we still do so. Because of our unique partial order preservation business, decur needs to maintain the state for the mapping. So we make decur a persistent actor, so that decur's runtime state can be recovered from its journal and snapshot. We journal decur's messages for changes to a Redis persistent store. We take snapshot to and from Redis persistent store. Now that we are set with the actor design, let's move on to our cluster design. Before we put together our cluster components, we like to keep tenants related business separated from general execution business. On the left, source of events can flow to the right. In the middle, we keep tenant related business logic, including multi-tenant support, fairness, elasticity, partial order preservation, and so on. So the real task execution takes place in the task execution box to the right. From a runtime topology, we like to call tenant-related business traffic controller, so boxes in the middle. And task execution business execution engine, those are boxes to the right. Tasks coming from the source flow into traffic controller in the middle, depending on the tenants. When it comes to task execution, the real execution takes place in the execution engine boxes to the right. So a tenant can choose to use one or more execution engine resources. And when the tenant releases its execution engine resource, the tenant's processing is paused. So in our design, we kept coming back to these general design guidelines. For distributed system design, always anticipate repeated messages and handle item potency when needed. So always anticipate repeated messages and handle item potency when needed. So with those guidelines and topology in mind, let's start our design for traffic controller. For traffic controller, we like to use Akka Cluster. So a cluster can have multiple nodes, those light blue rectangle boxes. And a node can have multiple shards, those rounded rectangle boxes. And a shard can have multiple entity actors. Those are purple tenant boxes, those are the entity actors. So under a tenant entity, we keep the actor hierarchy design from our previous actor design. So for execution engine, we choose the Akka cluster as well, and surprisingly, we started with exactly same cluster structure as we had in traffic controller. The only difference is the entity actor name. Instead of calling it a tenant, here we call it engine entity in execution engine cluster. Initially, this gives the team a big leverage since everything we learn while we building traffic controller can be applied to building execution engine cluster. This greatly reduces project complexity and risk in the beginning. As the team gets more mature with the Akka technology and the project gets more component integrated, we started tuning and optimizing traffic controller business and/or execution engine business. So this strategy proves to work really well and help us mitigate the overall project risk and people concern. So the cluster design is great for overall horizontal scalability, but how can we scale a tenant horizontally? So with our multi-cluster design, a tenant can dynamically acquire an execution engine cluster at runtime. So this way we can scale a tenant's business processing across not only JVM boundary, but also cluster boundary. How do we keep exec1's execution semantics for executing the task? As we mentioned before, we designed to anticipate repeated messages and handle item potency when needed. So we use at least one delivery mechanism to send a task from a tenant's executor in traffic controller to tenant's execution engine. So the real task execution takes place in the engine executor inside execution engine cluster. There, when executing a task, we check against a persistent store for item potency support. And when the task execution is finished, we again use at least once delivery to send back the task completion message. How about runaway task? Since we designed to anticipate repeated messages and handle item potency when needed, we can just employ a very low frequency timer to resend long overdue tasks from traffic controller. This way, we can easily recover a runaway task if there's any. So here I'd like to hand over to my colleague, Apurva, to share Akka experience.
Thank you, Pei. So obviously we had to go build all that, and during our build iterations or dev cycles, we had some learnings and experiences with Akka. We would like to share some of those experiences with you. Let's start off with shard allocation strategy. So the default shard allocation strategy is great and works as intended. And as you can see on the screen, all shards are spread out as much as they can. But when we introduced our own sharding algorithm, an additional detail was introduced along with it, which cannot be seen by the default shard allocation strategy. So here is how the shards would look like with our own sharding algorithm. The algorithm creates a fixed set of shards per DB, and the cluster is allowed to work on a fixed number of DB instances. This is done to guardrail the DB and the JVM. So in this diagram, for example, we have 5 shards per DB, and each DB is denoted by a color. Why is this additional detail important to us, or why does it even matter? In our system, the DB connection pools are allocated per JVM or node. Again, this is done to guardrail the DB resource. This means that under high load, if 2 or more shards from the same DB are on the same JVM, threads working on those shards will be starved for DB connections. This assumes that the work is greater than the number of threads, and that is greater than the number of available DB connections. To further drive this point, let's see how a new shard gets allocated with the default strategy. So ignoring the sharding algorithm, the default strategy would be to assign the new shard to node 2 or node 3. For this example, let's say it goes to node 2. And now let's see how that would look with the detail introduced by our sharding algorithm. So as seen before, the new shard is being assigned to node 2. But as mentioned before, this is inefficient. This is because the incoming green shard is allocated to a node that already has another green shard. So what do we do to fix this? We need to spread out shards from a DB as much as possible as well. So we went ahead and implemented our own allocation strategy to do just that. So this is how it would look like with our own allocation strategy. All shards from the same DB are spread out. And now let's see how new shards will be allocated with this one. So now we have an incoming green shard. This one will avoid node 1, 4, and 5 because it already has green shards. And the incoming shard has an option between node 2 or node 3. Let's say it goes to node 2. And once it goes to node 2, all the green shards are still spread out well. Next, we have an incoming red shard. This one would avoid node 3, 4, and 5, and has an option between node 1 and 2. And let's say it goes to node 1, and once it goes in, red shards are also still spread out well. Note that the total number of shards in each node is unbalanced, but this is still efficient for our use case. If the difference is larger than a threshold, the rebalance process kicks in. We use the default rebalance strategy, and that's good enough for our use case. Rebalancing will use our new allocation strategy to reallocate these shards until it is eventually consistent with our expectations. Just for an example, this is how it would look like with 6 nodes. The 5 shards now have more room to distribute themselves. And with 4 nodes, inefficiencies are inevitable, but these inefficiencies are also spread out well. So the takeaway for us here is really simple. If you have a new sharding algorithm that potentially introduces a new detail or a complexity, you might have to evaluate replacing it with a custom implementation if that really is the case. Moving on to cluster deployment and uptime. So we had a few concerns, more like annoyances. We saw that it took about 15 to 20 minutes for a cluster restart. We also saw that we had slow recovery for our persistent actors on a rebalance or a restart. And we noted that the overall journal size was about 10 GB per data center for Akka Persistence. So we asked ourselves, why was this happening? So we had dequeuers and executors to be persistent actors on both the controller and the execution engine side. For us, the sharding algorithm on the execution engine side enables us to create a lot of actors to the scale of about 10,000 per shard. And so in a stable environment, a 10 GB journal size was to be expected. And slow recovery time is a consequence of this large journal. And so what do we do to fix this? So we had designed the controller's dequeuer to be the brain for a dispatching operation. Also, the executor's state on the controller side was also being maintained by the dequeuer. Any default or previous state in the engine became irrelevant to us because it could be inferred from the task being dispatched by the controller's executor. So except for the controller's dequeuer, all the other actors were switched to be regular non-persistent actors. Again, this is of significance to us because, as mentioned before, our system creates a lot of actors on the engine side. And how did that help us? So we saw a significant reduction in total usage for our journal store. On screen, you will see 2 screenshots for Redis usage before and after deploying these changes. On the left, we have about 10 GB of used memory. On the right, it's about 44 MB. So the total reduction was about 99.6%. But this wasn't the only good thing that came out of this. Now that the engine takes only 5 to 10 seconds to restart, since the engine does not have to recover any state or rebalance or a restart. There's also no need to remember entities for the engine. As Pei mentioned before, we have a controller resend or a retry, which helps in lazy state recovery for the engine actors. The execution engine is also now stateless, since we do not have persistent actors there. This allows us to do rolling upgrades and have 0% downtime. All right, let's move on to back pressure handling. So our back pressure implementation uses a persistent queue for a buffer, and the flow control protocol involves 2 modes, pull mode and push mode, as mentioned before by Pei. We implemented this in 2 phases. In phase 1, we had a simple, effective implementation. In phase 2, we made an improvement on top of that. So let's look at phase 1 first. And we have push mode for phase 1. So in push mode, the enqueuer first pushes tasks to the queue. Then the enqueuer sends a message to the dequeuer saying that it has pushed a task to the queue. Then after the dequeuer receives that message, the dequeuer starts pulling from the queue until it has reached its capacity. And once it has reached its capacity, the dequeuer will send back a message to the enqueuer saying that, oh, go back to pull mode. For pull mode, the enqueuer still continues to push the task to the queue. And the dequeuer still continues to pull the task from the queue until the queue is empty this time. And once the queue is empty, the dequeuer will send back a message to the enqueuer saying that change to push mode. That was phase 1, by the way. So why is this inefficient? So we can see that the enqueuer always pushes to the queue, which means that DB writes are involved, and the dequeuer always has to read from the queue as well. Saving to the queue and sending these messages are 2 different steps right now. And these steps can be combined, and the task can be sent over to the dequeuer within that message itself. So here's phase 2. In push mode, now we have the enqueuer sending the tasks sending a message containing those tasks. And the dequeuer is accepting these tasks until it reaches capacity. Once it reaches capacity, the dequeuer sends back an intention this time saying that it is ready for pull mode. The dequeuer acknowledges that and also sends back another acknowledgement saying that, okay, I am in pull mode, you also change to pull mode. At the same time, once the enqueuer goes to pull mode, the enqueuer starts pushing tasks to the queue instead. Once the dequeuer receives the acknowledgement from the enqueuer, the dequeuer would also move to pull mode and consume the task from the queue until it has exhausted the queue. Pull mode is kind of similar with these additional acknowledgements, and so I won't go into detail to explain that. So what's the difference? Apart from the new acknowledgements, now the persistent queue is only introduced if and when needed. And so what did we gain out of that? So on screen is a graph of total writes to the persistent queue. We can see that we have drastically reduced these writes to persistent queue. The writes dropped to about 99.84% at the inflection point, as you see on the screen. This is when the changes were deployed. Note that the writes are still not 0, but they are significantly less. So what is a general takeaway for us from all this? So we look forward to identify potential improvements in a design and dev phase, and we come back periodically to check if this improvement is needed, or if it's a low-hanging fruit, or if it is required for any performance or other bottlenecks. And once implemented, we also periodically come back to measure and brag about it. So we had quite a few more Akka stories to tell, but I'll stop for time, and I'll hand it off to Daniel.
Thanks, Apurva. So as a significant part of this project, besides just working with Akka, our old legacy campaign engine was in a completely different language. So we had to rewrite about 50% of our total code base and make it work well with this system. And we made some mistakes and learned quite a few lessons on the way. So first, at a high level, just some of the lessons we learned. Parallelism is hard, but there's a couple of simple tricks that can make it much, much easier, especially working in a large team with many different components that eventually have to come together. So we'll come back to a couple of these points over the next slides. First, I'm going to talk about resource pooling. And as an example, I'm going to use database connections, but for any sort of external resource that has to be shared, the same principle should apply. Revisiting our legacy system for a second, as Dennis mentioned, it doesn't really make use of multi-threading. Instead, we have different processes, each of them single-threaded. And this made life really easy, because if you needed a database connection, you got it at the start of the process, you held it forever. There was no contention, no pooling, no sharing. Contrast that with a multi-threaded Java or Scala application, and suddenly there's a lot of contention. And our first instinct when rewriting our code base was to do a lot of more or less copy and pasting with some language translations. But this meant our lower level APIs were taking database connections already borrowed from a pool at the very high level of our application. And this leads to a lot of red space here, where a thread is blocked, not able to do any meaningful work until another thread gives up its database resource. We quickly saw this. We saw that our throughput was nowhere near what we wanted it to be. And so we said, we have to completely change our paradigm. And instead, we got into a model more like this. Here, each low-level API doesn't expect to get an existing database connection. Instead, it checks one out from the pool, quickly does its database operation, and returns it from the pool before doing any in-memory computation. This looks good. There's a lot less red on this slide, but we still didn't really get the throughput we wanted. And on closer inspection, we saw there's a missing piece of this picture, which is getting a connection from the pool and returning a connection back into the pool has a significant overhead, especially since we're doing very quick tasks. It was a high percentage of our execution spent on just overhead going back and forth with this connection pool. So yeah, our threads aren't blocked, but we're still not doing meaningful work with our CPU time. Finally, we found a compromise. Here, if one of our campaign actions needed to do 2 or maybe 3 database operations, we would say, okay, these first 2, there's not a lot of in-memory computation in between. So let's use a single connection for it, then return that connection, do some heavy lifting in memory, check out another connection, and do our third operation. And this way, there's more blocked time on our threads, but overall, we're doing more meaningful work with the CPU time we have, and so our throughput was able to drastically increase. Next, we found that the way we were doing updates in our legacy operations wasn't really scalable. And so first, some product behavior that we have motivating why we needed to make this change. In Marketo, anytime a lead object is changed by a campaign, we record an activity log of it for the marketers to look at. And this can be very important because here we see, okay, I have a lead, their product interest just changed to high. That seems very good until I look at the old value. It was very high, it's on the decline. So as a marketer, I'm gonna look at that differently than if it went from low to high. And in order to log these activities, we need sort of atomic updates, even when there are concurrent processes running. So our legacy system achieved this. Oops. I pressed the bad button. Our legacy system achieved this by freezing the record, checking the state of it to get the old value for the field we were going to update, and then performing the update and writing to that activity log. This is fine, it works, but it's really a pessimistic approach. And it penalizes any sort of concurrency, even if a different process wants to update a completely different field. If it's the same record, it's frozen until our update goes through. So in order to avoid this penalty, we use an optimistic update strategy, where we check the state of the record, we never lock anything, but we build into our update an assumption that that state is stable. If it isn't, our update will fail, and we'll keep retrying. This, of course, penalizes the case where there is another process concurrently updating that same field on the same record, but that's not a very common case for us. More often, different processes will work maybe on the same record, but on different fields. And so most of the time, we don't pay any sort of penalty, no matter what the concurrency is. To make this a little more concrete, in terms of MySQL updates, our legacy system would do something like this, where it uses a transaction, it selects some record for update, freezing that row until our transaction is done, and then it finally does the update, safely knowing that it knows the old value and has set the new value. Contrast that with our new system. We do a normal select, we don't lock anything, we don't use any transactions, but in our update, we build in an assumption that that state is still stable. Sometimes that assumption fails, and then we just keep retrying until we get to a stable state. And finally, I want to talk maybe a little less about reactive, but more about just a Scala pattern that becomes more important in a very highly concurrent system, and that's the loan pattern, which we found extremely useful for identifying problems in our code and enforcing good practices. So first, here's some procedural style code that's just getting a connection, using that connection to build a statement, and iterating through a result set. And I think we've all looked at code like this, but nobody really likes looking at it. It's a lot of boilerplate. It's hard to identify the meaningful business logic. It's hard to identify even bugs. Here, the result set never gets closed, but just looking at it, it's hard to pick that out. So contrast that with a loan style. And the way we achieve this is with a very thin wrapper class around all of our resource providers. So at the top level, that would be the connection pool, and then all the way down. The connection becomes a provider of statements. Statements become a provider of result sets. And these thin wrapper classes that we put around them provide some loan of the connection. So I never go to the pool and say, give me a connection and I'll return it to you later. I go to the pool and say, I need to use a connection to do this work, please do it for me. And then within the closure, the work that I submitted is done, and at the end, everything is automatically closed, and I'm given back the result. So the first advantage is, of course, safety. My connection is always closed. My result set gets iterated through automatically. That's really just a convenience, but it does make it easier to read and write code. Second advantage is it's easier to read and write code. I can quickly pick out the business logic here. I've got a SQL statement, I do something with the result set, and that's basically it. All of the boilerplate is hidden away within those wrapper classes. Finally, I can see what I'm using my connection for. I know the connection is open throughout this whole closure, so anything in here that doesn't need a connection shouldn't be in there. In this case, I'm doing some string concatenation holding a MySQL database connection. There's no reason to do that. So I can quickly identify it, and I can quickly fix it. I just move that concatenation outside of the closure, and now I know my database connection is going to be returned, another thread is unblocked and can do its database operations, and I'll do my in-memory concatenation without interfering with any other threads. In this case, it doesn't really matter, but in our campaign actions, we definitely were doing some very heavy lifting, CPU-intensive operations with a database connection in hand that was never being used. And so by identifying places like this in our code base and making that very simple change, just this to this, we were able to greatly improve our throughput. And so this is all fun. We had a great time working on the project, but did we get anything out of it? Why did we spend a year working on this? And the answer is we actually were able to greatly reduce our operational costs. Our legacy system for a group of about 200 tenants would run on 3 physical machines, pretty heavy-duty ones, with 40 cores and 32 gigs of RAM. For that same group of 200 tenants, we can now run on 8 virtual machines with only 4 cores and 8 gigs of RAM each. So using about 1/4 of the CPU resources and 2/3 of the memory, we still see a 20 times increase in the maximum throughput each of our tenants can get. Using less, we're able to do way more just by restructuring how we think about our code. We also have some takeaways about using Akka and using reactive patterns. Akka as a framework, we really appreciate the lightweight nature of it. A lot of our campaign actions do pretty heavy CPU computations, and so if our framework was also heavy, it wouldn't work. We wouldn't be able to run on the lightweight VMs that we want to. So having a lightweight memory footprint and CPU footprint makes it a viable choice for us. Aside from Akka, just the actor model in general, we found very useful because it encourages us to think about parallelism at design time. The concurrency is in between actors, and that means within an actor, when we're actually writing all of our campaign actions, you need to think about concurrency a little bit, but not that much. Concurrency is at design time and doesn't come up very much at development time, which is very useful, especially in a large team. For future improvements, we're very excited to do some auto-scaling for the bandwidth control that Pei had talked about. Currently, we're still on a more immature model of giving tenants more and less executors as needed, but we appreciate that the actor model allows us to sort of encapsulate that as a message that right now is being sent manually. In the future, there will be something monitoring it and sending that message automatically. Also, as Apurva mentioned, our execution engine has now become completely stateless, and so we're very excited about looking into using Akka streams rather than a raw actor model for it. And finally, if any of this sounds like something you'd want to work on, we are hiring. So tomorrow we actually have a talk from our VP and Director of Engineering, George Lowe, and Jane Liu. So they'll be talking more about the business managerial aspects of this, how we, as a team, made the transition from a legacy system into a new reactive system, and they can also give you more information about job opportunities. And with that, we're happy to take any questions. Are there any mics?
Do we have a microphone?
Thank you. When you were talking about fairness, as far as I understand, it's about fair resource sharing between different tenants, right?
Yeah.
And you're trying to achieve it by having similar number of executors per tenant. But does it mean that you've got no more executors than you have, for example, CPU cores per box? Because if you are deploying, say, 100 of executor units per box, some of them can be heavily loaded, some of them can receive completely no messages. Mm-hmm. How are you solving this kind of contention?
So actually, if we... Here's my mouse. Oh, if you can find one of the in-between cluster slides. While he's trying to pull up the slide, I'll try to answer. So our executors are more representing execution slots. So they're definitely not tied to any direct processing power. It's rather, for one of our tenants, we say, you can be working on at most, say, 100 tasks in parallel. And then those tasks are spread out among the execution engine cluster. So it's not so much blocking one of those slots as saying, for this tenant, we give you X level of concurrency. So here, the fairness and bandwidth is coming from this one to n on the left side, whereas the execution is done over here. So even if a task is blocking that executor slot for a long time, there's no real CPU blocking.
I can also add a little bit comments here. So we trust the underlying VM or OS does its good job in terms of fairness among all the threads. So that one we trust. So assume a tenant or among tenants, assume they use the very same execution engine resource. So the number of executors they get essentially is their execution bandwidth. So that's how we achieve the fairness for among tenants.